we will talk about evaporation and transpiration, which is you already know a little bit about it in our previous last 2 weeks, I guess, when we talk about hydrological cycle. There is this thing like evaporation, transpiration, and evapotranspiration. I already mentioned it, and I already talked about it a little bit also on our previous module when we talk about hydrological cycle. So yeah, this is the hydrological cycle that you already saw in our previous last 2 weeks, I guess. So the evaporation is in number 1, and then we got transpiration in number 2. And if we sum the number 1 and number 2, when evaporation and transpiration happen, it will be evapotranspiration. So yeah, today we will talk about evaporation and transpiration. What is evaporation? So the evaporation is when the water molecules on the surface, in this example, is in the water surface, water molecules on the surface, which is the water that we can see. And then there is a heat. So the water vapor molecules in the atmosphere, because of the force of the heat, there is changing in the molecules at first as water, and then it is evaporate into the atmosphere as an results of the force of the heat. So the factors affecting the evaporation process is meteorology and the type of evaporative surface. So here the meteorology is clearly related to the hydrological cycle. So it depends on its, for example, season. When there's a lot of sun, there are a lot of heat. So the evaporation will be bigger. And the type of the evaporative surface also play important roles in the evaporation process, because the evaporation is not only happen in the surface of the water, not only in the sea or in the lake, but also, for example, in the inside of the soil. It also can be evaporated because the water which is contained in the soil makes the soil is moisture, and because of the heat of the sun, for example, the soil can be dry because the water is evaporated. And yeah, the type of the evaporation, as I already mentioned, the first one is from the water surface, free water surface, for example, like in our hydrological cycle, it is from the ocean, the lakes, the river. That's evaporation from the free water surface. But there's also evaporation from groundwater, which makes the the moisture of the ground or of the soil, it becomes less and less because of the evaporation. So the water contained in the soil, which makes the soil moisturized, can be decreasing because of the evaporation. And for the evaporation from free water surface, we can calculate it, of course. there are various types of how to calculate the evaporation. First, by direct measurement. Second, with empirical equation. And the third, based on the water balance. The first one, direct measurement, we need tools. For this one, the tools that usually used is Atmometer and Evaporation Pan. So for the Atmometer, the principle is the evaporation is through porous fields or porous media. And the results is not absolute. So the evaporation data can be positive or negative. For example, like this, the evaporation gauge that usually used in the field. The atmometer is like this one, the left one, and the evaporation pan, because of its name, it's similar to pan. This one, it is located usually in the open area, open wide area. So it's not like easily disturbed by the other things or other people. So how the atmometer works? Usually the atmometer is made like this in the laboratorium. So in the picture is the auto atmometer. But principally, the atmometer works. At first, we pour water into the tube until it is full. So this is the tube. And this is the laboratory type of the atmometer, like the glass pipe. And then there is this water paper filter. And then there's this thing, and we pour water into the tube until it's full. And then we, on the open end of the tube, we insert this paper filter. This one is the paper. The paper is serves as a cover for the tube. So actually, this tube is a hole. There is a hole in this tube. So the water, we pour the water from here, and then we close the tube with the water and with the paper filter, and with this thing, and then we turn the tube over so that the paper covering at the bottom. So we turn the tube, and then we hang the tube on a branch or tree around the place of observation. So this is the laboratory type of the atmometer. The starting position of the water on the tube, we have to note that, and then we can know the evaporation by look at the changing of the position of the water in the tube. Like principally, the water in the tube will be decreasing because there's this paper filter, and there's heat outside the pipe glass. Of course, the water which is absorbed by the paper filter will be also dried by the heat of the sun. So the water will be decreasing, and then we can record the drop of the decreasing water level in the glass tube, and then we can know the evaporation rate by calculating the differences. This is the example for 15 minutes, but for the evaporation rate, we can calculate it per minutes or per hour. So this is the not the simple atmometer. This is the standardized atmometer. So the previous one is the simpler one for laboratory use. This is the one that that is used in the field, the atmometer, or sometimes people call it evaporimeter because it is used to calculate the evaporation. So the name is evaporimeter. Yeah, this one is also similar. There is this canvas cover. The differences is the this is the water reservoir. In our previous picture, it is the glass tube, and then there's a scale in the tube, and there's also this green canvas cover. The differences is it is not upside down. So when they already ready to calculate the evaporation, they turn it upside down so the water can be transferred to this canvas, and then because of the heat, the canvas will be dried, and then after that we can calculate the evaporation by the differences between the water level from the beginning until the end. For example, in particular time duration, 15 minutes or in 1 hour, and then we can know the evaporation rate. This is the more simpler one. For the previous one is the laboratory use, and then this one is the field use, and then this one is the homemade atmometer. You can make it yourself at home. This is from the plastic bottle. There is this plastic bottle, and then there is this things like fabric. So using this fabric, you can absorb the water until it goes up here, and there's this thing, this fabric circle here, which will be absorbs the heat from the sun, and then when it wet by the water here, it will also dry by the heat of the sun, and then from time to time we can observe it whether the water is decreasing or not, and then we can calculate the decreasing water, how many centimeters. For example, here we have like the orange area, this orange line here. It is the sign of the start of the water, and then after 1 hour maybe the water will be decreased in how many centimeters, and then we can know the evaporation rate of this area using this homemade atmometer. And beside atmometer, we can also use the evaporation pan, but there is no homemade evaporation pan. So this is the regular evaporation pan. So how to install this evaporation pan? As you already seen, the evaporation pan, because of its name, it is similar to pan. And to install this evaporation pan, there are three ways to install it. first you can plant it in the ground, so it becomes like groundwater thing, not groundwater thing, but it is immersed or planted inside the soil. And then the second one, you can put it in the surface of the water, so it will be floating on the surface of the water. And then the third one is above ground level. So the first one is below the ground level, planted in the ground. The third one is above the ground level. So it is you just put it above the ground, and the second one you float it in the surface of the water. So these three different ways can be used, depends on your necessity. Like if you need to calculate the evaporation of the lake, for example, yeah, you can float it in the surface of the water of your destination lake. And if you want to calculate the evaporation of the particular area, you can put it inside the ground, in the ground or above the ground. Like here, there's also disadvantages and the difficulties of this install ways of evaporation pan. The first one, if you immerse or plant it in the ground, you can eliminate the effect of radiation on the pan walls, because the pan walls will be inside the ground, inside the soil, and the heat exchange between the atmosphere and the pan. But the disadvantages, trash can go inside. It is difficult to install because you have to dig first, and then for the repairment, it's also more complicated. And if you clean it, and if there is leaks, it's also hard to find. And then it is also influenced by the surrounding plants. And so, as you know, plants has various types of roots. So if the roots is still like strong, and then it will be difficult for your pan to be installed near the plants or near the roots of the plants. And how about to float it on the surface of the water? Yeah, it is usually used for the lake or reservoir evaporation. So if you want to calculate the evaporation of the reservoir or the lake, usually you float the evaporation pan on the surface of the water. It is also close to the real number, which means it is really the estimation of the number of evaporation is really more accurate if you put it on the surface of the water than you put it above the ground level near the water area. But the difficulty, there will be splashing water go inside the inside the evaporation pan. It also more expensive because of the difficulties in installation and in operational, because it has to be floating in the center of the surface of the water, not in the border, so it can be more accurate. That's why it is expensive, because the difficulties of the installation and operational. And how about to put it above the ground level? Yeah, it is more economical than float it in the surface of the water. It's easier to install, to operate, and to maintain. But the disadvantages, the number of evaporation is greater than it actually is. So it's overestimate the actual evaporation if we put it above the ground level. So for example, for planted or sunken evaporation pan, there are 3 types, but the most commonly used is this type here, sunken Colorado. The second one, there is this sunken young evaporation pan. The differences between those types are the size. Usually it's different. It depends on the necessity and on the area available for this installation of the evaporation pan. For the young type, the size is 2 feet, or here we have the unit of feet and inches because it's using the American standard. So that's why. And then if we converted it into the metric standard, 2 feet becomes like 61 centimeters. And then it has height of 91.5 centimeters. It is closed by a filter with size of 6 millimeters. So the filters can be used as a safety net. So the trash is not going inside this planted pan. And the pan also has a coefficient. So if you want to calculate the evaporation, you have to use this coefficient, range of coefficient, so that you know the exact evaporation is how big is the actual evaporation compared to the evaporation calculated with this evaporation pan. And there is also this Colorado types, which has bigger diameter than the young sunken pan, but the height is smaller, 18 inch, and then it has fan coefficient of 0.75 until 0.86. The third one is BPI sunken pan. It has the biggest size of evaporation pan compared to the young and Colorado. It also has quite high height. Here we have like 61 centimeters, and it has the same pan coefficient with the young sunken pan. This is the type of the sunken Colorado pan. Usually the sunken one has the shape of rectangular shape, not the circular one, because of it, because it has to be sink below the ground level. So they think that the rectangular type or rectangular size is easier than the circular type. So here we have the size of 92, and then the height of 41 centimeters, and it also has like safety area of 5 centimeter. So the maximum water level will be this 5 centimeters below the sunken pan, and there is this measuring device here, which measure the changes of the water level from time to time. So from the changes of the water level, we can know how big is the evaporation. The second one is the floating type, floating pan. This shape is similar to the class A evaporation pan, which is a circular one, and it is floating on the surface of the water or the lake, and it has coefficient of 0.8. And for the ground level, it is actually what you saw in the picture, in the previous picture here. This one is the evaporation pond, which is on the ground level. As you can see in the picture, it is located in the ground, on the ground. And then it's made of iron, not galvanized and unpainted. That's why the color is still looks like original iron, and it has diameter of 122 centimeters and height of 25.4 centimeters. It is located on a wooden frame as high as 6 inches, and it fills with the water to a depth of 20 centimeters. So it has like 5.4 centimeters safety level, and the water level is measured every day. The evaporation is calculated as the differences in the water level. And yeah, as I already told you before, it is usually overestimate the evaporation. So the evaporation which is calculated is far bigger than the actual evaporation happened. It has span coefficient of 0.6 until 0.8. So this is the floating pan. As you can see, as its name, floating pan, it is floating in the water. If you want to look for the evaporation of the lake or of the reservoir, you can use this floating pan. Yeah, and then it is usually located in the center of the lake or of the reservoir. And this one is the class A evaporation pan, which located on the ground. This is the wooden thing. And then this is the measuring device. And this is the filter area to prevent something going in inside the evaporation pan. Because as you know, this evaporation pan is located in the widely open area, and there will be also like wild animals in this area, for example, like birds or something like that, and it also can disturb this evaporation pan. That's why it is used. It use this filter or snap to prevent it happening. Yeah, this is the sketch of this evaporation pan. The diameter of 120.7 centimeters, and it has the water depth of 20 centimeters. And the height of the evaporation pan is 25 centimeters. And the wooden has like a height of around 5 centimeters. And this is the measuring device. Yeah, so this is the standardized size of the class A evaporation pan, standard by United States, USSR, and yeah, it has area of 3,000 centimeters square, and it has a height of 60 centimeters on the wall, and it is deeper in the middle. So the size is pretty depends on the standard that they use. So it can be varied. It based on the standard or depends on the area where the evaporation pan is used. But for the shape is usually the same. So if it located on the ground, it has to be circular one. But if it's located sunken inside or below the ground, it usually has rectangular shape. So regarding the measurement, there is this measuring device here with the measuring needle here. And how to measure it depends on the conditions. So there are 3 measurement conditions. The first one, so as you can see, the evaporation pan is open. It has open area. All the 3 evaporation pans has open area. Like if it's raining, it can go inside the pan. So these measurement conditions, the first one, if it doesn't rain, but the water must be added to the pan. For example, here, if the water is not so, if the water is because of the evaporation, the water become less and less each day, and there is no rain, so the water can be too little or measurement condition. So it has to be additional water inside the evaporation pan, and then we can calculate the amount of the evaporation by the amount of the water added to the pan multiplied by the pan coefficient. If it doesn't rain, but if it's rain and the water must be added to the pan, we can also calculate the evaporation based on the amount of the rain plus the amount of the water added to the pan multiplied by the pan coefficient. And then if it's rain, but the rain is too much, so we have to throw away the water from the evaporation pan. So if it rains and then the water must come out of the pan, we can calculate the amount of the evaporation based on the amount of the rain minus the amount of the water released from the pan multiplied by the pan coefficient. So this is where we use the pan coefficient when we want to calculate the evaporation, the amount of evaporation. So there is this empirical formula to calculate the evaporation. There is C as a constant, and then ES as a saturated water vapor pressure at temperature T, and then EA, actual vapor pressure at temperature T, and then there is the FU, function of wind speed. This general empirical formulation can be used to calculate the evaporation, but if all of the variables is known. So to make it easy, there is already people who observe the evaporation, and then they compare the evaporation of the actual evaporation, and then compare it with the empirical equation, and after that they can obtain modify empirical equation based on their observation. For example, here we have the actual evaporation equal to 0.35 times ES minus EA times 0.5 plus 0.54 times U2, as in U2 here is the velocity of the wind in the height of 2 meters in 1 day, like the average of the wind in 1 day. This is can be found in the data, like if you remember, we already talked about meteorology in our previous meetings. So the data can be obtained from the meteorology. It is also included the wind velocity. So this wind velocity can be obtained in the data. And after that, if you know the wind velocity and then you know the ES and EA, you can calculate the evaporation. And if this formula is used for water evaporation in the pan and lakes, it also can be written as follow. As here, we have EAP is the evaporation of the pan, and then EAD is the evaporation of the lakes. And after that, we can assume the wind speed and the constant, the C, is the same. So the FU and the C is the same. So we can simply the equation, we can make it simple, becoming like this one. So from the previous equation here, we have C and FU. If we have the same C and the same FU, the difference will be only the ES and the EA. That's why it becomes like this. The evaporation will be the factor of ES and EA. And then after that, we can know that this one is the Pan coefficient. So the Pan coefficient is the differences between the evaporation in the pan and the actual evaporation happen. For example, this one is in the lakes. That's why we have the pan coefficient on each evaporation pan, which is different, depends on where it is located. Like we have evaporation pan located in the ground. The coefficient is different with the evaporation pan located inside the ground or above the water surface, because it is the comparison between the actual evaporation and the evaporation happen in the pan. And this evaporation also related to water balance. If you remember, we already talked about water balance in our previous modules. This water balance means that the evaporation equals to the inflow minus outflow plus minus the change of the storage. So here, if we have an inflow and then we have an outflow, and then there is a change in the storage, we can calculate the evaporation based on the variables that we already calculated before. So, yeah. Is there any question?
Yes, I would like to ask a question, Miss, from the previous slide. Yes.
Yeah.
What is the P and D in EAP and EAD?
P and D.
Yeah, there's EAP what is the P means, and EAD, what does the D means?
P is means the evaporation in the pan. P is
Okay.
pan. D is the lakes, because it is translated from the Indonesian slide. So lakes is danau. So it becomes the D one.
Okay. Thank you.
Yeah.
That's all.
Okay. Yeah. So we already talked about the evaporation from the water surface. And now we will talk about the evaporation from the soil surface. So this is the evaporation happen in the soil. So it is related to water contained in the soil, or we can call it like soil moisture. The soil evaporation is not the same with the free water evaporation, because it depends on the type of the soil. As you know, there are a lot of types of the soil. There's also the soil which is dry, and there's also the soil which contains a lot of water. It is similar to the mud. So soil saturated with water, and then if it evaporates, it can affect the elevation of surrounding water level in the soil. If the soil surface is not related to the groundwater level, and the evaporation is small, so it depends on the rainfall. The amount of the water in the soil, it depends on the rainfall. So if the rainfall is big, it means the soil contains a lot of water from the rainfall. The evaporation will also be big, because the water contained in the soil, which is originated from the rainfall, will be evaporated. It will be different if the soil has relation to the groundwater level. So if there's no rain, the water contained in the soil, it's only the groundwater. So by means the evaporation will also evaporates the water contained in the groundwater. And if it's not depends on the rainfall, whether if it's rain or not, the evaporation will keep happen. If the soil surface is connected to capillary area, the evaporation will also be big, because this soil surface contain water from the soil, or groundwater, or soil moisture. It has supply from the groundwater. So this is the lysimeter. Lysimeter is the tools that can be used to calculate the evaporation from the soil surface. So this one is different tools than the tools that we use to calculate the evaporation from the water surface. From the previous one, we used the atmometer and the evaporation pan. It also can only be used for the evaporation from the water surface, not from the soil surface. For the evaporation from the soil surface, we have to use this thing, lysimeter. This lysimeter can calculate the evaporation from the soil surface based on the inflow. The inflow is usually from the rain or from the water contained in the soil. And there is this outflow, because as you know, the groundwater is flowing flowing inside the ground with the destination to the lakes or to the sea. If you remember the water cycle, hydrological cycle, there's this water inside the ground that we cannot see because it's not seen on the surface. It is also flowing inside the ground, and then it has the final destination in the lakes or river or the sea. And it becomes an outflow here. So the inflow from the rainfall minus the outflow, which is water flowing to the river or the sea, and then plus minus the change of the storage. Here we have water storage as in the previous one, we have storage of the water as in the lake, in the reservoir, but here we have it as a soil moisture. So the water storage is the soil moisture, which is which contains water, which makes the soil moisturized. What if the soil is planted? So if the soil is planted, there is plant. And then the evaporation of the plant is called transpiration. So the evaporation from the soil, which has plant, is the evapotranspiration, or here we call it with ET. So the evapotranspiration is the evaporation and the transpiration. This is the smart lysimeter. So this is the automatic lysimeter. It can calculate how big is the transpiration happens in this in the soil. Like here, we have a tube. Inside the tube, there is the soil, and in the soil, there will be plants. Not always, but usually, if we plant it, so the number that lysimeter calculated is the evapotranspiration. But if it's only the soil, the number that the lysimeter calculated is only the evaporation. So after we talk about the evaporation, we can also talk about the transpiration, because it's here. We have the smart lysimeter. It can also calculate the transpiration because of the soil. We can also plant it. We can also plant it with the plants in the soil, so it becomes the transpiration. And if we calculate transpiration, it depends on the meteorology, the water supply, and the types and the phases of the plant growth. So the measurement is depends on the which season are we in, and then which temperature is in that area, and then how much water supply in the area, if there is rain, how big is the rain, if there is water for irrigation, how big is the discharge, and if the soil is moisturized, how big is the soil moisture and which type of the soil. And then it also depends on the type of the plant, because it's different if we planting plants which needs a lot of water with the plants which doesn't need a lot of water. The transpiration rate will be different. And the measurement of the transpiration usually performed in the laboratory, and the tools, there's there are two tools, the photometer and the phytometer. And the photometer, usually called transpirometer, and this is the experiment calculating the transpiration. This is a typo, transpiration. And this is the simple photometer, which is used in the laboratory. And there is this observation using plant leaf. Here you can see the plant, and then there is water, and then the scale, air bubble, and there is also water here. And the observation are done in various conditions. Here you can see the first condition is with sunlight, and the second condition with shade, so a little bit of sunlight. And the third one is with darkness, without sunlight at all. And then the fourth one is when fan is placed in front of twig in the sunlight. Here is the twig, and then there is a fan with the wind. So it because it is done in laboratory, so there's no natural wind. So they make the wind using the fan, and they place it in front of the plant here in the sunlight. And there's also time taken in each condition is 5 minutes. And then they read the initial of the bubble here. There is a scale in the air bubble, and then the initial reading, and then the final reading is after 5 minutes. And then there is this distance traveled by the bubble, so the changes or reading of the bubble based on the scale. And we can see here the distance traveled by the bubble. The biggest one is when the fan is placed in front of the twig in sunlight. So the transpiration is bigger if there is sun and there is wind. It has a little bit difference. It has little differences with the condition with only sunlight without wind. So yeah, sun has a big part of the transpiration, but sun plus wind has the biggest change in the transpiration. So if there is no sunlight at all, with the darkness condition, there is no change in the bubble. It means there's no transpiration. And if there is a little bit of sunlight here with the shade condition, yeah, there is also a little bit of transpiration here. So this is the simple transpirator or transpirometer, or here is simple photometer. How to calculate the transpiration rate? We have to calculate the area of the entire leaf first. Here we use the twig, how many leaves it has, and then we have to calculate all of the area of the leaf as a sample area. And then we have to weigh the leaves at the beginning and the end of the experiment. So the changes of the weight of the leaves, because the water contained in the leaves will also be weighted. And the next, we can calculate the transpiration rate using the formula. Here we have the initial weight minus the final weight, and then divided by the area of the leaves. And how about if the transpiration and the evaporation happen in one place? As I already mentioned, usually it called the evapotranspiration, and the measurement in the laboratory or in the field is using the lysimeter. So here the lysimeter, this one, this lysimeter can be used for calculate the evaporation, but it also can be used to calculate the transpiration because of the soil can be planted here. And that's why this lysimeter can be used to calculate the evapotranspiration. But because we are in the class, we cannot only use the this thing, this lysimeter, smart lysimeter. We have to use the more difficult one. That's why we have to learn about this formula for calculating the evapotranspiration. This formula is based on the experiments. As you know, if the formula is based on experiment, usually it is empirical formula, and usually it is named with the people with the people who's done the experiments before. Here is the list. So formula to calculate the evapotranspiration, and there are various formula based on the experiments, and there are also various experiments. For example, here the first one, the formula using daily average air temperature data. So usually the experiment is based on the data that they use, and it is also based on the data which is available. Here we have to understand clearly which formula that we can use if we have the exact amount of the data. For example, if we have the daily average air temperature data, we can use this formula from Lowry Johnson, Thorne White, and then Lenny Criddle. So there are three formulas. If we have this average air temperature data, and how about if we use the daily average air temperature and the solar radiation? And from that data, we can use the formula from these people. Like there are 5 formulas. And then using daily average air temperature and humidity data, the previous one is the solar radiation. And how about if we use the humidity data? We can use the formula from these 4 people. And how about if we use complex formula? We can use this complex formula, which means there are a lot of data that we have to know. For example, here we have the Penman, Christensen, and Van Bevel. And the formula that often used for irrigation, it is related to other types of hydrology. This is for the irrigation. And the formula that often used is the Thorne White, Lenny Criddle, Penman, Turklang-Beinmund. And for the exact formula based on experiment here, we can use based on the data that available, or we can also use based on our necessity. For example, if we want to calculate the evapotranspiration for irrigation, yeah, we have to use this formula, this for last formula. But if we want to calculate only the transpiration, we don't have to do it for the irrigation. Okay, we can use the other one. For example, here we have the Blenny-Criddle equation. In this class, we will only talk about two methods, which is Plenum and Spendman method, because these two is the most commonly used. So we will only talk about these two in this class. But if you want to look for other method, you can look for it by yourself using the literature. As you know, today we can look for other things easily using Google. So if you want to know the other method or the other equation, feel free to do so. Here we have the Blaney-Criddle equation. It is used to calculate the potential evapotranspiration. Here we have PET. And which data that we have to know. For example, here, if you want to use the Blaney-Criddle method, you have to have the mean monthly temperature, monthly percentage of daily hours, and then plant growth coefficient. These three data you have to know if you want to use this Blaney-Criddle equation. The formula is originally like this: U equal k multiplied by T and C divided by 100, where K is the plant growth coefficient, T is the mean monthly temperature, and P is the monthly percentage of daily hours. Based on the data that we know, we can see that the potential evaporation that we calculated here will be in the monthly, because the data that we use is based on the month, and we can calculate it monthly, and then for 1 year we can have 12 different potential evapotranspiration based on the month. And if you want to calculate using the other units, because it's based on the US units, here for the original formula is in the inch. And if you want to use the metric units in millimeter, you have to modify the equation to be like this one. And here we have the K, P, and also P divided by 100 millimeter. And the K is the Kc multiplied by Kt, where Kt is the 0.0311 T plus 0.24. And Kc is the plant growth coefficient for each plant. Like if you want to calculate the amount of the K plant growth coefficient, if you have a lot of plants, for example, you can calculate it with using this Kc multiplied by Kt. And the other one is the Spendman method. This Spendman method can be used for area where the following data are available. So it has more data requirements than the Blaney-Criddle method. For the Spendman method, we have to know the data of the temperature, humidity, the wind, and the duration of the solar radiation. This duration of solar radiation means duration of the sun shines in 1 day. Like for 1 day we have 24 hours, and then we have the duration of solar radiation, which means the duration of the sun shines in 1 day. And for the for the Spendman method, we will talk more about it on our next meeting, because this Spendman method is a little bit complicated, but it will be useful for the next, like for this Spendman method is used in the irrigation, usually for evapotranspiration in irrigation. So it will be useful if you know this method clearly. And for the data, actually it can be found easily if you know the like if you want to know for the exact location, the data is as I know, it's available, like it is free access in the PMKG. So I think you can like access it easily. Here we have the original Spendman, and it is found in 1948. The name of the person who found it is Spendman. And the original Spendman equation is estimating the amount of water loss due to evaporation that occurs at the surface of the water. The experiments, as you know, this all empirical equation is based on experiments, but for the Spendman is carried out in the UK, and it is resulted in the crop coefficient ranging from 0.6 in winter to 0.8 in summer. Yeah, because of this, Spendman is the experiment is carried out in the UK, which has like 4 systems. It's quite different with the with our region, so we cannot use this original Spendman method directly. Like in the Spendman equation consists of parts of energy based on the solar radiation, and parts of aerodynamics based on the wind and humidity. That's why we need to know these 3 data. Because of it is because of the experiments is carried out in the UK, so for this Spendman equation, it has to be modified so it can be used widely in worldwide area. That's why there is this Spendman equation modified by FAO. So here is the equation that we will use as a Spendman equation. So for using this Spendman equation, we can calculate the evapotranspiration. For the evapotranspiration, we have to calculate the C. C is the adjustment factor to compensate the effect of the weather during the day and the night. And then we have to know the W, the weighting factor. The Rn is the net of radiation netto. And we have to know the Fu is the wind speed function. And as Es minus Ea is the differences between the saturated vapor pressure and the actual vapor pressure average at the average temperature. So this data can be found like here. For the next lesson, we will talk more about this Spendman method or Spendman equation. Let me show you the materials first for the PDF, because it is a little bit complicated. So you have to like look for it more thoroughly. But actually the data is already there, like you can use it directly. Let me share it first. So for this Spendman method, there is this like separated materials. only consists of Spendman method because it has a lot of data that you have to know. So there will be a lot of like table. From the table, you can find which screen that I share. Okay, I have to share this screen first. So for this Spendman method, I think you already saw the screen, right? For this Spendman method, there is this equation. This is the form of the equation that we will use that I already told you in the previous slide. And then for each of the variables, there's this description of each variables and how to calculate each variables. We have to talk about it more truly in our next meeting, but I will share this material so you can read it by yourself first, so that when we talk about it in the class, you already know a little bit of it, and you will know, I think you will understand it more clearly when we have the class on the next meeting. So for the net radiation, and then here we have adjustment factors, and yeah, here we have like the data, and then based on the altitude and latitude, and for each altitude and latitude, you have to know the you will know the vapor pressure based on the table. So if you want to look for evapotranspiration on exact location, for example, you already know the height of the location, you will know the vapor pressure based on this table. For example, here we have the wind function, and then the weighting factors based on the altitude and the temperatures on your area. And then here we have the extraterrestrial radiation, and it is based on the latitude also. You have to know like Indonesia is located in which latitude, and then your area is on which latitude, and then in which month that you want to calculate your evapotranspiration. Here we already have like from January until December. It depends on your necessity. And this one is the sunshine hours, like in one day, how many sunshine hours are there for different months in different latitudes. So it depends on the area and for which months are you going to calculate this evapotranspiration. And there's also this adjustment factor here. There are a lot of tables. That's why I want to share it first before I explain it to you. So you will see a little bit of it first by yourself. And if you have any question, you can ask on our next meeting. That's what I hope. So if you have any question from our today's meeting, from materials that I taught you today, if there's a question, you can ask directly now, because the materials for today, it's already finished, I guess. Yeah. Okay. If there's a question,